So today we're looking at equivalent representations of trig functions. What this means is we're going to be looking at the full set of trigonometric identities. So first off, the first identity we're going to see is the Pythagorean identity. And if you consider we've got a right angle triangle in the unit circle, and if we were to just try and use Pythagoras' theorem on this, the length of the x coordinate is cosine theta, the y is sine theta, and the hypotenuse is 1. So the square of the two sides would be the sine squared theta plus cos squared theta is equal to the hypotenuse squared, which is 1. And this gives us a very useful formula. It's called the Pythagorean identity. It's your formula number 1. You're going to have 1, 2, 6. You're going to have about 7 or 8 formulas to memorize today. Yep. So here is the Pythagorean identity. First and foremost, you memorize this one. It's fairly straightforward and easy to remember because it's if you understand the unit circle, and obviously, hopefully you understand Pythagoras' theorem, it's very straightforward. We can use that to make some alternatives. So our first alternative, we're going to use that formula to show that question. We're going to show that tan squared theta plus 1 is sec squared theta. So to do a show that question, if you remember, we start on the left-hand side. We say what the left-hand side is equal to, tan squared theta plus 1. And then we make some changes. So let's change tan squared theta using tan theta equals sine theta over cos theta. And that will give us sine squared theta over cos squared theta. We can change 1 as well to be cos squared theta over cos squared theta. I choose this because I want a common denominator. I see that the denominator of the other one was cosine squared theta, so I make the necessary changes there on that one. So then we can combine these two, and we've got sine squared theta plus cos squared theta all over cos squared theta. Well, the numerator is simply equal to 1. And 1 over cosine squared theta is going to be secant squared theta, which, just squeeze it in here, is the right-hand side. You have another alternative as well in this form. This is another alternative. Okay, so looking at the inverse trigonometric identities on this one, we can, if we make the adjacent equal to x, we can use Pythagoras' theorem to find the expression for the opposite in terms of x, using Pythagoras' theorem. We see that the triangle is labeled this, this, and this. So then, if we say that the cosine let me just write it for you on this one. If we say that the cosine of theta is equal to the adjacent over the hypotenuse, then that simplifies to the cosine of theta is equal to x. If we take arc cosine on both sides, we will get theta is equal to arc cosine of x. Now, for the sine, in this case, the sine of theta is equal to 1 minus x squared. And that means theta is equal to arc sine of 1 minus x squared. This leads us to an identity that both of these two are the same. So we end up, they're both equal to theta, so we end up with arc cosine of x is equal to arc sine of root 1 minus x squared. And this lets us move between sine and cosine. We end up with two inverse trigonometric identities, and depending on which side you start by calling x, you get two different versions of the same formula, here and here. I think on this course you will use these two less. On this course you will use these two less. Now, comes into, this is the important ones. This is the important ones. We have, is it 6 formulas here, or is it 8? We call the first two the compound angle identities. So these are the compound angle identities. There's another name for them. And these ones are the double angle identities. On this course, we'll call them the sum and difference identities. The sum and difference identities. Seems like a lot, seems like it's very complicated. Let's first have a go at just using them. We'll flip backwards and forwards between the different pages and pick which ones we're going to use. So, here in this question, we have to find an equivalent expression to this. We have to find an equivalent expression to this. Notice the 2 at the beginning. Notice the 2 at the beginning. We've got sine of something. Look at how the angles are the same angle. Look how the angles are the same angle. So let's go back and look at our formulas. Now, notice how the sum and difference identities, the angles are not the same. The sum and difference identities, the angles are different. The angles are different. In the double angle identities, the angles are the same. So, firstly, you're going to have to try and choose which identities am I using. The more you practice with these, the more you get familiar with them, and you spot it much quicker. So we see that the angles are the same, and we have a 2 there, and there's just 2 terms. This is the most common one. It's clearly this one. You can see that it's very close to this already. 2 sine theta is equal to 2 sine theta cos theta. This is the double angle identity for sine. I would say it's the most common. So the double angle identity for sine, if I write it down, bring it onto this page for us, is sine 2 theta is equal to 2 sine theta cos theta. So what we've got there is the right-hand side, isn't it? If we rewrite it, what would it become? Sine of pi over 7. Or, let's go the long way. Sine of 2 lots of pi over 14. Sine pi over 7. It's going to be this one. Okay, so what I notice first on this one is we have a double angle here. Very clearly can see the double angle, and it's cosine. We have a double angle for cosine. Now, we could use the formula sheet and we'll get the one that we want. But typically, if I'm trying to memorize it, if I'm trying to memorize the different formulas, I only memorize one of the cosine ones. If we look back at the cosine one, this one's really confusing in that there's 3 different forms. Well, I only memorize myself this bit. I only memorize this bit. That one looks a bit like the Pythagorean identity, but a bit backwards. And that's how I remember it. What you then do is you can replace sine and cosine in each one by using the Pythagorean identity. And I'll show you how we can do that. So I'm only going to memorize that one. So here on my formula sheet, I memorize that the cosine of theta is equal to, and it's a bit backwards, so we start with cosine squared instead of sine squared. We have a minus sign instead of a plus sign. And this is the angle identity for the double angle identity. Now, we also know that the Pythagorean identity tells us that sine squared theta plus cos squared theta equals 1. This means we can rearrange it into any form. If we want cosine squared theta, then that's going to be 1 minus sine squared theta. And if we want sine squared theta, then that's going to be 1 minus cosine squared theta. So we can substitute that into the into the double angle identity for cosine wherever we wish. So on this question, we have 4 times the cosine of 2x. So that's going to be 4 times cos squared theta minus sine squared theta. And then inserting each one, we could say 4 times, I'm going to get rid of cos, so I'll have 1 minus sine squared theta minus sine squared theta. Or I could have 4, and then this time I'll substitute out the, I'll substitute out sine this time, and I'll get cosine squared theta minus 1 plus cosine squared theta. Now, each one is, this one here is wrong. This one is the double angle identity for sine. Let me just show you what they're thinking here. This is sine 2 theta equals 2 sine theta cos theta. This is this formula. So this one is equal to 4 sine 2 theta. This is the double angle identity there. This one's just messing us with a little bit with this one. This formula is 4 bracket 1 minus 2 sine squared theta. So you can see here, if I was to factor that, I would have 4 bracket 1 minus 2 cos squared theta, or x. That's just messing us with that one, trying to get you confused between the two. This last one over here, that's the Pythagorean identity, or you're just missing the minus sign there. It doesn't have that minus sign. It's ever so close to looking right, but it's not quite. This last one here, if I rearrange it, will give us 4 cosine squared theta. Oh, sorry. This last one will give us 4 bracket 2 cos squared theta minus 1, which when we expand the bracket will give us 8 cosine squared theta minus 4. This is the correct answer. But it's playing with all of the different formulas because they all look more or less right at first inspection. You have to be quite careful with these. MCQ. No, both. This will be big. It'll be in MCQ and FRQ. Because you can tie it with equation solving. If you want to make equation solving hard, you mix these in as well. Sahan, do we have to play Tetris? Oh, okay. All right. Okay. So this is one of the double angle identities. So the double angle identities, this one, if we look back to our formulas, we've got, notice how the angles are different here in this one. We've got a different angle here and here. We've got the same different angles here and here. We've got two cosines, and then we've got two sines. So if we scoot back to our formula sheet, which one looks like this? The double angle identity, the compound angle, the sum and difference identity for cosine. Now, did we have a plus or a minus? We had a minus. So we are going to want this one here with this one here. Notice how the pluses and minuses are different. So we are going to use the formula, the cosine of alpha, which one we got? We got that, plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. So for this question, our formula is going to be, we've got the cosine of pi over 8 plus pi over 16 is going to be the cosine of 3 pi over 16. Do we have that one? Yeah, let's see. All right, these formulas seem impossible to memorize, all of these. Seems impossible to memorize all of these. It's not going to be too difficult. So we know what Pythagoras' theorem looks like. So we start with this one. This is sine squared theta plus cosine squared theta equals the hypotenuse. Think of the unit circle. Think of Pythagoras' theorem. That one's easy. It's very, very common. We use this one a lot. This one is a fairly simple looking formula, and it's the most common that we use after the Pythagorean identity. And it looks quite simple. So it gets a little bit trickier then with double angle identities. So for cosine double angle identity, I only memorize one. Unless I'm doing it regularly, then they sort of stick in my head. If I'm doing a worksheet of these, it doesn't take me long for me to load up. When I've done one or two questions, I'll load up the other ones. But if from year to year and month to month, I don't remember them. This one looks like the Pythagorean identity. This one looks like the Pythagorean identity, but not. We get cosine squared theta minus sine squared theta. It sort of looks like the Pythagorean identity, but backwards. Next up come the sum and difference identities. So sine of alpha plus minus beta. So we're adding and subtracting them. Now, I remember it like this one. Sine is normal. Cosine is the one that's always a bit backwards. Because it's the cosine. It just always feels like it's secondary to sine. Sine starts at 0, 0 and goes up and down. Cosine's always a little bit shifty. So the sine one's fairly straightforward. So it's just the sine of alpha, the cosine of beta, and the plus and minus is the same. So we just expand it looking like this. Now, all you have to remember then is that the cosine's a bit shifty. So when we have the cosine, everything gets changed a little bit. Cosine always comes first on the cosine formulas. Notice how cosine comes first here, and it's going to come first here on this one. So this is the cosine of alpha, the cosine of beta. It's and then we make this upside down. Cosine's always a bit backwards. This one's upside down. And then we've got sine alpha, sine alpha, sine beta. And then that's it. That's all the formulas, if you memorize these ones. Yeah. For the compound angle identity, there's no 2's. Oh, I see. Sorry, I messed up there a little bit. I messed up here. Obviously, I'd written the same thing twice. What happened there? I'd written the same thing twice. So it has to be different. It has to be sine beta cosine alpha. Or, I think it was written in our formulas earlier as it was the cosine alpha sine beta. Thank you. I nearly messed up. My computer is just warning me it's going to do an automatic restart, an update. So I'm like, oh no, not in the middle of my video. So I started panicking a little bit there to try and get through this. I feel it's going to cut off on me. All right. So let's have a go at a problem-solving question. Have a go at this one for yourself. Okay, so we need to find a value for sine 2 theta. So the formula sine 2 theta is equal to 2 sine theta cosine theta. Here in our diagram, we have a right-angled triangle where this length is 13, this length is 12, this length is 5, the right angle is there, and theta is here. This means that the sine of theta is opposite over hypotenuse, 12 over 13. The cosine of theta, adjacent over hypotenuse, 5 over 13. So this is going to be 2. The sine of theta is 12 over 13. The cosine of theta is 5 over 13. 2 times 5 is 10, times 12 is 120. 13 squared is 169. Have I got the exam style question? 2 minutes for this one. Okay, let's have a look. Let's have a look on this one. So we are to solve where f of x is equal to a half, which means that the cosine of x plus pi over 6 is equal to a half. Let's expand that using the compound angle identity. Now it's cosine, so we get cosines first. Cosine x, cosine pi over 6. It's cosine, so everything's backwards. Sine x, sine pi over 6 is equal to a half. Now the cosine of pi over 6 is root 3 over 2. The sine of pi over 6 is a half. Everything's over a half. We can get rid of that. Root 3 cosine x minus sine x equals 1. So, do we have one that matches that? Believe it to be A. Yeah? That one matches. The other ones all look like they almost match, but not quite. Okay, that is it for today.